Okay, let's play linear ODEs into state space form. When we start a state space problem, we got to define state variables. This model over here is for a car, linear representation of a car, where P is the position of the car, F is the friction of the car, theta is the input, and P dot is the output. So we're just going to put that here. And also, we said theta was the input, so U equal to theta. Okay, first thing we have to do is define our state variables. We have two of them to work with. We have the P position and F the friction. P has a maximum derivative order of 2. F has a maximum derivative order of 2. Therefore, we are going to have two state variables for each of them. Let's go for the P's first. X1 is equal to P, and X2 is going to be equal to P dot. X3 is going to be equal to F, and X4 is going to be equal to F dot. State variables defined. Let's take their derivatives. X1 dot is equal to P dot, which is equal to X2. X2 dot is equal to P double dot, which in order to find, we have to do some manipulating over here. We got to divide everybody by M, so we're left with P double dot over here. So it's going to be alpha over M P dot plus F over M. Now, P dot is X2, so this is really alpha over M X2 plus F is X3, so this is 1 over M X3. Now we'll go X3 dot is equal to F dot, and F dot is equal to X4. Now X4 dot is going to be equal to F double dot, which, again, we're going to have to do some manipulating here. We're going to move these over to the right side, and that'll leave us with just F double dot. So F double dot is going to be minus A1 F dot minus A0 F plus K theta. F dot is X4. So this is really negative A1 X4. F is X3, so this is minus A0 X3. And theta is U, so that's KU. Now we have our state variables and our state variable derivatives defined. We can put this into our state space form. Remember, state space form, X dot equals AX plus BU, Y equals CX plus DU. We'll do it right here. X dot is really X1 dot, X2 dot, X3 dot, X4 dot is going to be equal to, A matrix is going to be a square matrix where n is the number of state variables. So that's going to be a 4 by 4, a fairly large one. And that's going to be times X1, X2, X3, X4. Don't get these mixed up with these. These are the derivatives now. These are just the states. And then this is going to be plus the B matrix, which is going to be n by 1 U and then we'll come down here for Y is going to be 1 by n, the C matrix, also going to be x1, x2, x3, x4, and this will be DE. So here's our empty skeleton of a state space model from this standard form. Now we just have to read what we got from our state variables and state variable derivatives to put it all into the model. So let's go through it. The x1 dot was x2. So in this one I'm going to have 0 for x1, 1 for x2, 0 for x3, 0 for x4. x2 dot had alpha over m x2, alpha over m x2, and 1 over m x3, and zeros everywhere else. And x3 dot had an x4, so that's going to be a 1 here and zeros everywhere else. And x4, negative a1 in the x4 slot, negative a0 in the x3 slot, and zeros everywhere else. And that was in the x4 slot, so that's going to be, we had a ku here, so it's going to be 0, 0, 0, k. Now y, the output, y we were told is equal to p dot, and we know that p dot is equal to x2, so it's going to be 0, 1, 0, 0. And that's how you go from multiple ODEs into state space form.